Howdy, y'all. Welcome back to Geography 110. For the next couple classes, or actually pretty much for the rest of the semester, we're going to be talking about geomorphology, which is how wind and waves and streams and rivers, how they all change the landscape, which is why I wanted to film the introduction out here today. Periodically throughout both this class as well as in future lessons, I'm going to be taking you down to the stream bed and showing you what rivers can do in terms of morphing the landscape. So let's go ahead and get started with today's lesson. All right, before we delve into the rest of today's lecture, though, I want to take a moment and reflect a little bit on the weekly recap. I'm currently recording this on Halloween at about 8:30 at night. Hopefully y'all have more exciting Halloween plans than I do. But looking through the forum responses, I can see that a lot of people are concerned about mass movements. And frankly, that's a legitimate concern. If you are a little bit shaky, no pun intended, on mass movements, then that's something we need to address because we have assignment 3 that's going to be due in 16 days. So let's talk about mass movements. Mass movements, and just sort of give a little bit of a recap here. A mass movement, mass wasting, I use those words interchangeably. And what do they mean? Well, it means that there's a massive kind of erosion event that occurs on the landscape. You have a lot of land that moves. There's generally some sort of disruption to nature that takes place. But the main thing that's associated with mass movements is the movement of land and the translation of land. So there are 3 main types of mass movements. We have falls, slides, and flows. And we talked about each one of these in great detail, but I'm just going to take a little bit of time. We're going to walk through this. So under falls are when materials break away, usually from a cliff, and they sort of fall off the side of the cliff, and then they create a bit what's referred to as a talus slope. A talus slope, of course, is just the debris, the soil, the rocks, the sand, the material that gets piled at the base of the cliff. Now, there are 3 main types of falls. We have rock falls, debris falls, and earth falls. They all do the exact same thing. The only difference is the size of the materials that's falling. For a rock fall, you can imagine this is going to be almost entirely composed of large rocks. Debris fall, whenever you have stuff falling off a cliff and it happens to have some rock and some soil, that's a debris fall. And an earth fall is predominantly soil, can also be sand, and generally doesn't have that much in the way of rocks. So rock fall, almost purely rocks. Earth fall, almost purely soil, sand. Debris fall, kind of in the middle. What about slides? Slides tend to break away from the side of the hill and sort of move like a single mass. They act as sort of like a chunk that just happened to break off from the side of the mountain. There are 2 different types of slides. You have translational slides, which sort of creates a stepwise pattern as the material sort of falls away from the side of the mountain. And again, this occurs somewhat quickly, but not as fast as a fall, right? This is something that occurs, and it may be a little bit sudden, but it's not going to be quite like a fall or even a flow for that matter. So to get back to the point at hand, translational slides, that's when you have that stepwise pattern. Whenever it breaks away from the side of the mountain, it usually breaks away as a sort of rectangular prism, as a chunk that happens to fall off. Rotational slides, on the other hand, occur when there's a little bit more moisture. And what happens is that when it breaks away, it sort of breaks away and creates a bit of a sphere, for lack of better words, a spherical chunk that falls out of the side of the mountain. I know that there's a lot more sort of technical way to describe it, but I think that's a good sort of difference between the 2. Translational is going to be in a slightly drier environment, and it's going to be that stepwise pattern. Rotation is going to be sort of like a sphere that breaks away from the side of the mountain. All right, the third big type of mass movement is a flow, and that is a continuous movement of earth and material that flows downhill like a river. And I showed you that video in class from Aconcagua, that debris flow that was coming down off the side of the mountain. Now that's a version of a flow. So if we think about falls, we have three different types of falls based on the type of material that's falling. For flows, it's the exact same thing. We have three different types of fast flows that are defined by the characteristics of that flow. So you have a rock avalanche. As you can imagine, that's a flow that's composed almost entirely of big rocks and boulders. You have a debris flow, which is that video that we saw a little bit, or when we saw a couple classes ago, the video of the earth and material flowing off the side of Aconcagua down in South America. And then we have a mud flow. And a mud flow is very dangerous. It's mostly composed of soil, and it's flowing off of the side of the mountain, coming down at high speeds. But frankly, these three flows, rock avalanche, debris flow, mud flow, they all operate pretty much the same way. They operate as a continuous movement of earth and material that sort of acts like a river, even if it doesn't have much moisture. The mud flow obviously will have a little bit of moisture, but the rock avalanche, odds are it's not going to have hardly any moisture associated with it. So those are the three types of fast flows. There's also two slow flows. There's a slow flow that's called a creep, and there's a slow flow that's called a solifluction. Now, in reality, the mechanics that are occurring with the creep and solifluction are practically the same thing. They have something, they're both are dependent upon temperature. Creep mostly occurs in sort of slightly drier landscapes. And what it is it's just the particle, the soil basically rises up a little bit whenever it gets warm, but then whenever it cools down, it contracts. But instead of contracting back into the same place it was, it contracts downhill slightly. So in effect, a creep is the earth just moving downhill, sometimes only a centimeter or two per year. Solifluction, it's the same speed of movement, about a centimeter or two per year, but the mechanic is slightly different. Instead of talking about thermal expansion and thermal contraction and falling downhill, you're talking about freeze-thaw. So whenever something freezes, like you have a particle of soil that freezes, it's going to expand out. And when it does that, it rises up a little. But whenever you have the spring thaw that comes along and that particle of soil thaws, it then sort of descends down the mountain. You have the force of gravity acting on it. And so those are the two versions of slow flows. If y'all have more questions related to that, feel free to hit me up an email or go ahead and ask Critty too. We're here to help you, and especially related to assignment 3, we want to make sure that you understand these mass movements. All right, moving on to fluvial geomorphology. So for the last couple classes, and frankly, I'd say as we were talking about weathering, we had slowly made that transition away from endogenic systems. And endogenic systems are systems that originate inside the surface of the Earth. We've been talking about endogenic systems whenever we're talking about plate tectonics and earthquakes and volcanoes. These are systems that are not necessarily dependent upon the sun. They're not dependent upon anything that really occurs much on the surface. Most of that occurs on the interior of the surface. Weathering sort of exists in that middle ground between an endogenic and an exogenic system. Weathering is dependent upon precipitation, but is ultimately very dependent upon gravity. Gravity being the most important driver of certain aspects of weathering, whether that's like a creep or solifluction or a flow. Gravity plays an important role in that. Now, though, weathering also has some characteristics of exogenic systems. And exogenic systems are processes that happen on or above the Earth's surface, that changes the Earth's surface, and that may incorporate an energy source that does not come from the Earth's core. So when we begin to think about chemical weathering, for example, right? In our last unit, that was sort of an example of exogenic system, right? You have a geologic rock, and because of its consistency and because of the air, it may react with the air and therefore begin to change its chemical composition. As we move into this latter part of the course, we're going to be talking almost exclusively about exogenic systems. And these are systems that are wind-driven, or river-driven, or tide-driven, or glacier-driven, right? These are systems that are going to have dramatic impacts on the Earth's surface. Okay, geomorphology. We've been talking about geomorphology. What is it? Geomorphology is the study of the Earth's surface landforms, such as their origin, evolution, form, and spatial distribution. Today's class, as well as for much of this week, we're going to be talking about fluvial geomorphology. After that, we're going to be talking about aeolian geomorphology, how the wind shapes landforms. Then we're going to go back to glacial geomorphology. And then we're going to finish up this class on coastal geomorphology. All right, fluvial geomorphology is, like I said, that's how rivers change landscapes. Fluvial geomorphology is a super important area of study for geographers because it plays a major role in human existence. I mean, you talk about the many culture hearths, or the place where culture began 5, 6, 7,000 years ago in Babylon and in Mesoamerica and in China. These culture hearths, the beginning of civilization, really began around rivers. So rivers provide that way to bring people together. They provide transportation. They provide agriculture. They create the necessary ingredients to support large populations. And so that's why geographers are really interested in rivers and the way that they can impact landscapes. And another reason to study rivers is because rivers are always changing. And that's something that we're going to be taking a look at towards the latter part of this class, as well as in Wednesday's class. So why do we study geomorphology in general? Well, we study geomorphology because of the way that you can have certain hazards, right? Locating landscape hazards such as landslides or coastal erosion or desertification, right? These are all sort of landform processes that are intimately related to geomorphology. What about climate change? Well, we see system processes are really changing in relationship to the changing temperature, changing precipitation, whether there's a glacier present or not, or even the melting of the ice sheets. We've been sort of skirting around these topics, but climate change, geomorphology and climate change are closely interlinked. And whenever you have climate change, that's obviously going to change the surface of the Earth in many different ways. And then finally, it's really important to study geomorphology because we need to understand the impacts to nature. How can a morphing landscape change the vitality of a forest, or impact the ecosystems that live on a sand dune, or so many other, or even how a hermit crab will survive in the tide, right? Understanding geomorphology gives us another way to understand nature. All right, so fluvial geomorphology, simply stated, is just how water erodes away the landscape and then deposits that land somewhere else. That's it. I mean, and frankly, that's what geomorphology pretty much encapsulates too. But if we talk about fluvial geomorphology, we're talking about rivers and streams and how they erode one landscape and then they deposit that sediment elsewhere. So erosion, for fluvial geomorphology, this means just the way that the river is going to be weathering down those materials that are in the river. You can see these rocks here in this example. This is a photo, I believe, from central Texas, right? And you can see these rocks, they're smooth, they've been weathered down. The sediment, as a result, has been pushed downstream. It could be over here in this riverbed, or it could be, frankly, in the Gulf of Mexico. I don't know. Deposition. Now, deposition is just how that stuff that's been eroded, the little bits of rock that came off here, how that gets deposited somewhere. Does it get deposited on this riverbank over here? Does it get deposited in the floodplain up here? Does it actually go all the way down to the Gulf of Mexico? Erosion, deposition. Frankly, that's all there is to fluvial geomorphology. But there's a lot more details that can be learned through those two metrics. All right, this class, this particular lesson, I hate to tell you, is going to be a lot of vocabulary. And one of the first bits of vocabulary that you need to know about is a drainage basin, or a watershed, or a catchment. Frankly, they all mean more or less the same thing. And a drainage basin, in layperson's term, just represents the region from which a river gets its water. And I don't mean like water from the sky, but whenever water hits the ground, where is that water going? Which river basin is it going into? And we can have nested scales in relation to river basins. So, for example, I have an image of the Cape Fear river basin right here. The the Haw River, for example, is going to have a different catchment basin or catchment watershed than the Deep River, or the Northeast Cape River will have a different catchment than the Cape River. But if we if we consider the entire Cape River, right, this area that's in sort of Manila yellow, that whole area sort of represents the drainage basin for the Cape Fear River. So we can say, okay, for a creek or a drainage ditch, that the watershed is going to be really, really small. For the Mississippi River, it's going to be humongous. And frankly, we can actually see the Mississippi River, its drainage basin sort of stretches all the way up, back over here, and sort of back over towards the northeastern part of the United States. And it's really quite amazing. All right, so when you have a drainage basin, it's going to be separated, right? The river or the water that's going to flow into the Haw River is going to be different than the water that flows into the Deep River. Now, why is that happen? Well, it's because there are drainage divides. So you can sort of imagine with your mind's eye that there's a divide somewhere between the Deep and the Haw River. And on one side, the water's going to flow down to the Haw River. And then on the other side, the water's going to flow down to the Deep River. The exact same thing happens with every single stream and river and creek that you can imagine. There are some divides that we like to talk about that are big, what we refer to as continental divides. And these, the great continental divide that we talk about in North America is this one that stretches all the way from near the Mexican border all the way up to northwestern Alaska. And what does this great divide imply? Well, that says that any precipitation, any snow, any rain, any time something happens over here that creates precipitation, water is going to flow either into the Arctic Ocean, the Atlantic Ocean, or the Gulf of Mexico. But on this side, on the left side of the red line, anytime you have rain, snow, any sort of precipitation, that water is going to flow either into the Bering Sea or into the Pacific Ocean, which is, of course, a part of the Bering Sea, right? So it's going to flow west. Anything over here is going to flow either east or south. Everything over here is going to flow towards the west. And so that's what we mean by a great divide or a continental divide. There are other sort of subcontinental divides. We can talk about the Eastern Divide, for example. So you can see North Carolina is broken apart as a result of this. So you have areas west of the Appalachian Mountains. Any water that flows on the western part of the Appalachian Mountains is going to flow into the Gulf of Mexico. Any water that hits the eastern side of the Appalachian Mountains, well, that's going to flow into the Atlantic Ocean. So we have these sort of minor continental divides that are all around. The one of those things that you need to keep aware of is that if you have a small change or a small sort of modification in one part of the system, that can have dramatic effects downstream. So, for example, if you had a mountain that was that traditionally, precipitated water towards the Gulf of Mexico, but then a dam breaks or something causes there's a landslide, and the way that the mountain gives off water changes, then that water is going to go down on the western side. It may go towards the Pacific Ocean instead. So that's going to dramatically change the way that the precipitation or that water is felt, right? If we have less water going to the Gulf of Mexico, that means that there's less water available for farmers and ranchers in Colorado, New Mexico, Texas, Oklahoma. But then you would have more water going to Las Vegas or Los Angeles or Phoenix. In terms of drainage basins that I want you to be aware of, the one that I want you to be kind of most aware of is this one here. This is the Cape Fear Drainage Basin, and this is the drainage basin for Chapel Hill. You can see Chapel Hill would be right around in here in southern Orange County. And so any water that comes off of the university, it flows eventually into the Haw River, and then from there into the Cape Fear River, which then eventually flows into the Gulf of Mexico. All right, what about internal drainage systems? These are also referred to as endorheic basins. So what happens is that you have a drainage basin, but the water doesn't reach the ocean. Instead, it goes to a central location where it either evaporates or infiltrates down into the aquifer. Some of the examples that we've come across before would be the Great Basin, for example. And here I can show you in this particular photograph here. This sort of brownish polygon here is the Great Basin. So any water that flows or originates within this Great Basin is not going to leave the Great Basin. It's going to stay there in the middle of the continent. We also have the example of the Caspian Sea, as well as the Dead Sea. You may have heard that the Dead Sea is so salty that it's impossible to sink, just about. And that's because there's a lot of water coming in, but there's no water going out. It all evaporates. And so all the salt gets sort of concentrated in there. Some of the metrics that we apply to catchment areas or to watersheds, again, mean almost the same thing, is going to be two things. You're going to have the basin area, and that's just the total area. So if we were thinking back to that Cape River example earlier, that's going to be that sort of manila E color. That's just expressed as a unit of area, like square miles or square kilometers. The drainage density is the total length of all the streams and rivers in a drainage basin divided by the total area, the basin area. That drainage density is really helpful in knowing about the runoff potential of a river and can help also keep track of desertification. So if you see the drainage density changing, then that could be a sign that either an area is becoming more arid or less arid, depending on which way the drainage density metric is going. So we have this example right here, and you can see, I believe this is from Colombia, is where I got this image. So this drainage density is, you have a lot of rivers in this small basin. So that means that there's high runoff potential, there's high drainage density. So there's basically the soil is such that it doesn't take in much water. It all sort of flows on the surface. Whereas down here, you can see there's a lot fewer branches for this particular part of the river. And so that indicates that the geology is different, right? The soil is able to take in a lot more water. What are some of the patterns that we see with drainage basins? I'm just going to kind of go through these in sort of quick detail. We have 5 different patterns that we're interested in. We have dendritic patterns, parallel patterns, radial patterns, rectangular patterns, and deranged patterns. And so by a pattern, I mean just how does it look from space? These drainage patterns help us understand a little bit more about the river's characteristics as well as its geology. So starting with a dendritic pattern, we see that a dendritic pattern is sort of like a tree-like pattern. Here's an example from Wikipedia that I stole, and you can see it sort of looks like a tree branch, right? This is the most common form of drainage system, this dendritic pattern, and it demonstrates that the geology is relatively homogeneous across the entire drainage basin. A parallel pattern almost always occurs on a steep slope or bands where there is weathering resistant rock with soil in between. So here we have an example from one of my photos from Alaska, and you can see we have parallel sort of drainage occurring here off the side of the mountain. In this particular example, we can see that there are parallel stream basins here. This isn't due to the slope of the mountain. Instead, it's due to the fact that this area in between is a little bit more resistant to weathering away. Just a little bit more. All right, we have radial drainages. This generally occurs whenever you have drainage off of a central point, thinking of volcanoes, mesas, high, tall mountains that are in isolation. Here's a photo I took off of Google Earth, right, a satellite image, and you can see that you have the river is draining off, or rivers, plural, are draining off in all directions. Rectangular drainage is uniform resistance to erosion, but generally occurs associated with jointing. And this most often occurs, frankly, around strike-slip faults. So talking about the San Andreas Fault. And this is, again, I took Google Earth over to the San Andreas Fault, and you can see it immediately, right? You have this river here, and then it drops into this fault. And then this river here, same thing, sort of dropping into this fault, and the river itself may drain out back over this way, or it may drain off to the side, but you can see it sort of moves in a blocky rectangular pattern. A deranged pattern occurs whenever you have drainage that's occurring, but there's no coherent pattern. And it usually occurs whenever you have some sort of like uncertain geologically complex area. So you can see here we have a little bit of a fault here in this Google Earth satellite image, and you have a particular sort of almost dendritic kind of drainage pattern here, and then boom, it changes and it's no longer dendritic. It's almost parallel in appearance. This area right in here would definitely be qualified as a deranged pattern. All right, let's go ahead and continue on with our study of fluvial geomorphology. So we've talked a little bit about drainage patterns. We've talked about some of the more qualitative, if you would, kind of ways to explore drainage patterns and fluvial geomorphology. Let's get into a little bit more of the quantitative side. And I realize this is some of the first times that we're encountering math formulas in the second half of the semester. And I'll try and tell you which ones you need to keep an eye on. For example, that one that we just saw on drainage basins. Let me see if I can pull it up. I want you to know about this drainage density formula, but its odds are you're not going to have to calculate anything associated with that. As for the stream flow characteristics, basically trying to determine discharge, yes, you're going to have to potentially, I'm not saying it's required, but odds are you might encounter a question in which you might have to calculate discharge on the test. So just be aware of that, and I'll try and signpost which formulas you really need to know and which ones you just sort of need to know about. All right, so discharge. When we talk about discharge, we're talking about how much water is moving through a river at any given time, or a stream, or even a bar ditch for that matter. And so discharge is purely just a volume of water per unit time. And what you do is you multiply the channel width by the channel depth, right? So width times depth, that gives you an area, and then you multiply that area by the stream velocity. And so here we have an example here, right? You have a depth right here, you have a width right here, and you have the velocity of the water moving through that little area of the river. And you just do that for basically every single little subsection within the river. And if you were a fluvial geomorphologist, you would go in and you would use some calculus and integrate across slopes. And I'm already giving some of y'all who aren't used to math some headaches. Don't worry about it. What I want you to know is to know this particular formula. Q discharge equals channel width times channel depth times stream velocity. This is frequently reported out as either meters cubed per second or feet cubed per second. And so, again, and you just sort of calculate it out for each little subsection of the river. And that tells you how much water that river is discharging, for example, into the ocean or into a lake, which can be very useful if you're a decision maker and trying to figure out how much water to allocate to each citizen. All right, some of the rivers with the greatest discharge, if we look across the world, the largest river in terms of discharge would be the Amazon River. In the United States, it's almost a virtual tie between the Mississippi River or the St. Lawrence River in terms of greatest discharge. And then in terms of greatest discharge in North Carolina, the largest river is going to be the Cape Fear River, which is, of course, the same river that runs near University of North Carolina. This is the apparatus that you use to capture one way of capturing basically stream discharge. You can see if you ever drive along the highway and you see one of those silver boxes and it's like right next to the river. I know I pass a couple almost every day whenever I go into town. What it is it's just a box that has a satellite antenna that's reporting data, and then you have a little tubule that runs out into the water and tries to capture how much water is moving through that intake valve there. It's not critical that you know how this system works, but I think it's sort of fascinating. And if you've never seen it, just sort of keep your eye out as you're driving around. You'll probably notice at least one or two near your house too. So how do you measure the region of the highest velocity in a river? Well, you look for an area that's near the surface at the region where it's usually the deepest. So if we were to look here at this this is a photo that I took of the Pecos River almost 15 years ago. And so we can see clearly deep down into the river. We have some big boulders on the sides. There's a few boulders in the middle, but not that many. This river is flowing downhill in this direction. And so we can see that there's a sort of a pretty deep pit right in there. So if we wanted to measure the stream velocity of this river, we would stick our measurement device right here, right underneath the top of the water, maybe about 6 to 12 inches underneath the top of the water. Why don't we stick our measurement device at the bottom of the river? Or why don't we measure on the sides of the river if we're trying to get max velocity? Well, frankly, it's due to friction, right? Because as that water is moving over rocks, or as it's moving near the bottom of the river, or as it's scraping against the side of grasses, it's going to slow down. So that area that's in the center, or at least the area that's in the deepest part of the channel, and just a little bit below the surface, that's going to be the area where you're receiving the least friction of all. So let's talk about stream flow characteristics in relation to discharge. So discharge typically increases the further downstream you get. So for example, if we were to go back to the Haw River example, which I'll do real quickly, we can imagine that these little tributaries into the Haw River, up here you're going to have less discharge, right? Because it's a smaller catchment area. You're only catching like this little bit right up here in the northern part of the river. So the discharge there is going to be completely different than at the mouth of the Cape River, where it empties into Cape Fear River, where it empties into the Atlantic Ocean. Where it empties into the Atlantic Ocean, the discharge is going to be quite extraordinary. Up here in the upper reaches of the Haw River, or the headwaters of the Haw River, odds are the discharge is going to be relatively small. So that's what you typically encounter. But that's not always the case. No, some streams are exotic streams in that they have decreasing discharge as they proceed downstream. Now this typically occurs in an arid region. So if you have a river that starts in the mountains, but then as it continues down towards the ocean, it goes through a really hot, dry region. Odds are it's going to lose a lot of water due to evaporation. And so we have this situation with the Nile River, for example, right? The Nile River originates somewhere in the highlands of Ethiopia, most likely. And then it travels downstream and goes through the Sahara Desert. Well, a lot of water is going to evaporate while it's in the Sahara Desert before it gets to the Mediterranean. Here I have a photo from the Rio Negro, which is a river in the southern part of Argentina, central Argentina rather. And as I'm flying over, you can sort of imagine that this begins up in the mountains where it's lush and green, but it's traveling through the really almost desert landscape of Patagonia, and it's experiencing a lot of evaporation. So the discharge right at the base of the Andes Mountains might be a little bit different than, say, the discharge by the time it reaches the Atlantic Ocean. Here in the United States, a good example of a disappearing or of an exotic stream is going to be the Rio Grande, right? In the highlands of New Mexico, where you have the headwaters of the Rio Grande, you usually have a lot of discharge, especially right after the snows begin to melt in March, April, and May. But it travels through the Sonoran Desert and the Chihuahuan Desert, some of the driest, well, not the Sonoran Desert, the Chihuahuan Desert. And so it's traveling through some of the drier areas of North America. And so by the time it reaches the Gulf of Mexico, the Rio Grande has lost a fair amount of water and just to evaporation. So one of those graphs that you need to be aware of in a way that we can measure discharge over time is a hodograph. And so the National Weather Service actually does a fantastic job of measuring a lot of the rivers and streams that you would encounter day in and day out. And they give the flow here, and this is 1,000 cubic feet per second. So you can sort of relate this back to the discharge formula that we were using earlier. And so this particular river gauge is on the Haw River near Pittsboro, about 15 miles south of Chapel Hill. And a hodograph, like I said, all it does is keep track of flow. And so you can see that the Haw River was flowing at about 1.3, or 1,300 cubic feet per second as of about Thursday evening. But then on Friday afternoon, there was a big rainstorm that came along, and that caused the hodograph to pop up. That caused the Haw River to rise up. And so briefly, the Haw River was discharging about 6,300 cubic feet per second of water. And the National Weather Service predicts, this is the forecast here, predicts that it will be back down to maybe 1,000 cubic feet per second by this coming Thursday. So this is a hodograph, a way to keep track of flow and discharge. Okay, so that's talking about basins and that's talking about stream flow. Why don't we talk a little bit more about the type of weathering, the type of ways that a river can actually change the landscape. And this occurs, like I said earlier, through erosion. So we have the hydraulic action, and that's just erosion due to water rubbing up against a surface. So as we can see here in this example from the Pecos River, a photo that I took 15 years ago, this river is flowing over rocks. As it flows over rocks, just by the mere fact that it's water, it's going to be pounding against the side of that rock, and odds are that rock is just going to begin to erode away. That is what's referred to as hydraulic action. We also have another form of erosion that's taking place, and that's abrasion. Abrasion is when you have rocks and boulders that are in the river, such as these here, and what they do is they flow downstream and they're going to scrape against other rocks. And as the one rock sort of scrapes against another rock as it's flowing downstream, that's going to create a little bit of erosion. You know, some of those rocks, or some of the sediment in those rocks is going to give way and flow downstream. And so we often see examples of abrasion in the form of very smooth, kind of smallish rocks found in riverbeds. That's sort of the quintessential example of abrasion. That's a sign that you've had basically like sediment that's been suspended in the water that kind of flows past that rock, and it acts almost exactly like sandpaper, smoothing down a rock over time. All right, you've heard me use this word a lot in this lecture, but let me give you a little bit of clarification. Sediment is naturally occurring material that is broken down by weathering. So if you have, say, for example, that abrasion, which is just like the sediment that's coming off of the side of a rock as it's being broken down by the stuff that's suspended in the water. That is sediment, right? That's just broken down rock, little pieces of sand and dirt, or little bits of rock that are floating in the river. Sediment transport is the movement of sediment by any fluid or fluid-like substance. So we'll be talking a little bit more about sediment transport, especially in the context of wind and glaciers. But in terms of water, we would like to think of this in terms of sediment load, which is the amount of solid material that is being currently carried by a stream. There are lots of different types of sediment loads, but we're going to be focusing on three. And I'm sorry, the PowerPoint sort of cut this off a little. We have the dissolved load. And so this is sediment that's so small, it's been broken down almost into its molecular structures, right? It's very, very, very small. Can't even see it. So that's dissolved load. But you also have suspended load. And this is the material that gets kind of ground up, and it may make a river look kind of yucky brown. That's because you have a suspended load. You have some sediment that's a little bit larger than the dissolved load, and that's actually sort of visible to the eye. And then your largest bits of sediment is going to be the stuff that's floating along the bottom of the river. And that's referred to as bed load. This stuff down here, these bigger rocks that are down here. Now, the bed load can move via two different ways. It can move via traction. It can move via saltation. Traction is just the scraping or rolling of a rock or pebble along the bottom of a river. So it pretty much stays in contact with the bottom of the river all the way. Saltation, on the other hand, is whenever a rock is just big enough that it can actually be levitated by the water, and it sort of jumps along, it sort of hops as it moves downstream. That's what's referred to as saltation. For those of you who study Spanish, saltar, to jump, it's basically the same idea. Saltation is just sort of the jumping of little bits of rock as it moves downriver. Okay, talking a little bit more about that vocabulary, we're going to be talking a little bit about stream gradients. And so a stream gradient is just the way that a stream sort of drops in elevation over time. So you can see here, this is a very steep gradient. The river is dropping down very, very quickly, right? There odds are there might be some waterfalls or something in these upper headwaters over here. Whenever you get to a gentle gradient, right, the slope is very gentle. The river's characteristics are going to change a little bit. It's not going to be quite like this dendritic pattern. It's going to take on a more wavy, kind of like a sine wave look as it starts heading towards its final destination. We're going to be talking a lot more about this wavy appearance and what that means in our next class. The longitudinal profile is looking at the stream's gradient mapped over distance. So seeing, basically just seeing that elevation and how it changes over the course of the entire river, from its headwaters all the way down to its mouth. We also see a little bit of headwater erosion, and this is another keyword that you have to be aware of. So in certain locations, it may sort of look like the river is eroding upstream as opposed to downstream. So this is a photo I took, or not a photo I took, this is a Google Earth image that I found as I was flying through Google Earth. And this is a Taos Regional Airport in New Mexico. And you can see here that you have these streams, and it sort of looks like that, in fact, as there is erosion, the erosion is actually going upstream. The river sort of looks like it's kind of growing upstream. This is what I'm referring to as headwater erosion, the apparent view that the stream is eroding upstream, right? It looks like it's eroding upstream as opposed to scraping away and making this area deeper. So one of those topics that I think the textbook really sort of fails to explain adequately is the idea of the nick point. So we're out here at the creek bed. You can see, you have water. It comes down through this culvert, passes under the fence here, and continues on downstream. But as it comes through here, it encounters a layer of bedrock that you can see right here. Now, what is a stream to do? I mean, it needs to go downstream, and it also sort of needs to go downhill. So as it flows over this bedrock going downstream, it actually creates a little bit of a waterfall, right? And you can sort of imagine whenever there is a lot of precipitation, you have a pretty large waterfall. And so as the water flows off of the side of this rock, it's going to fall down here and hit the secondary rock in here. And as it does that, it creates a little bit of an eddy. And that eddy eats away at the sediment that's right in here. So this right here, as well as that over there, right, as well as this right here, all of this is referred to as a nick point. And over time, we can expect that as the water flows over and as it creates that sort of gyre, that eddy, as the water flows over this rock here, over time, that sediment's going to eat away. And eventually, when enough of this sediment is gone, and the force of gravity is strong enough and creates sort of enough downward pressure or force on it, as well as, just a bunch of water sort of stacked on top of this bedrock here, eventually it's going to crack off and and float downstream, which is what we see here. Right, we can see pieces of what was once this bedrock has already detached and fallen off. So we can imagine that with time, this nick point will actually begin to continue to migrate backwards, going back upstream. And with it, of course, the waterfall will also go back upstream with time. So what happens when mountains begin to form around a stream and you have that orographic uplift? What happens is that the stream, if it's in the headwaters, right, the stream is rejuvenated, right? That river that may have been in this sort of quasi-equilibrium state or sort of on its way to being in an equilibrium state, if you have a mountain that sort of thrusts up the river, then that river is going to have a little bit more power, it's going to have a little bit more erosion. And I love the way that geologists and geographers refer to this, rejuvenation, right? The idea that this river now has life again. And this occurs occasionally, especially in areas where you have active mountain buildings such as Tibet or those places where we have the converging tectonic plates. Your textbook talks a little bit about the Grand Canyon example where there was probably a river that was already there, but as the Rocky Mountains formed and as this whole area in northern Arizona, southern Utah, and western Colorado all sort of went through an area of great uplift, that sort of changed the way that river acted, and the headlands became, or the headwaters rather, became rejuvenated. Now down here, what happened is that the river it was on its sort of particular course, and so it was both eroding downwards as well as sort of setting its course, and it set it sort of firmly in stone. So even as these mountains rose up around the Colorado River and the Grand Canyon, the river itself the river itself continued to erode away the landscape and create this very deep canyon. This is referred to as channel incision, when a stream continues to cut deeper and deeper and deeper into its own channel. And that's like I say, sometimes just due to pre-existing geology, but oftentimes it sort of is a marker that some sort of rejuvenation or mountain building event took place. All right, what do we have in the docket? Assignment 3 is still ongoing, and I'm going to keep harping on y'all to hopefully take a look at it before the due date. It's due, I believe, November 16th, or it's, I believe, due the last day of class. In our next class, we're going to be examining meanders, that sort of sinuous wave that we saw earlier. And this is a very common characteristic associated with rivers. We're going to be interrogating that a little bit more. I just want you to be aware, if you look at the schedule, it says readings and videos forthcoming. Go ahead and just ignore that. Just focus on those 3 pages that we have already set out for you there, pages 433 for 435 for Friday. You don't need to do anything more than that.